Good morning, everyone. Thank you for joining the online class of the Unit Operation 1. So today we're going to discuss about the pumps and gas moving equipment subchapter, which is subchapter 3.3. So I put the two files. On the left one, I opened the fourth edition of John Coples. And then on the right, I also open my PowerPoint so you can see one by one, but I hope that you can also open your own book so that you can make a note during the class. Okay, so I'm going to start with the subchapter, pumps and gas moving equipment. So to make a fluid flow, it requires driving force or energy. As you can see here. It can be supplied by gravity, or it can be supplied by mechanical device such as pumps, blowers, and others. Now, the driving force will increase the velocity or the pressure or the elevation of the fluid. So if you can imagine, the driving force can be supplied by gravity. So if you have a vertical pipe, actually the fluid can flow directly from the top to the bottom of the pipe, without any driving force, without any mechanical driving force needed. Only by gravity is enough. However, if you want to make a fluid flow from the bottom, to the top, or on the same level, then you require this mechanical device, to increase the velocity of the fluid, the pressure of the fluid, and finally to increase the elevation of the fluid. Okay, so in this part, we will discuss about pumps and gas moving machinery. So what are the difference between the two? So pumps, okay, for the pumps, it's actually to move the incompressible fluid such as liquid. Okay, so pumps refers to a machine or a mechanical device to move the liquid, while gas moving machinery, sometimes we know it as fans, blower, or compressor. It's actually to move mostly compressible fluid such as gas. Now, fans discharge large volume of low pressure gas. So if you see an exhaust fan maybe in your home, it will discharge a large volume of low pressure gas. If you come close to the fence, you can still feel the pressure increase. However, the increment is not too big. While for the blower or compressor, it discharges gases at higher pressure. So if you come near blower or compressor, you can feel a strong wind. Because it discharges gases at higher pressure. Now, since the fans discharge large volume of low pressure gas, so since it works at low pressure and the density of the gas does not change significantly, sometimes it can be classified as an equipment to move the incompressible fluid as well. So some books regards fans as a mechanical device to move incompressible fluid as well. Because of the small pressure change between the inlet and the outlet. So that makes the density of the fluid, the density of the gas does not change significantly. But some books will regard fans still as the gas moving machinery, because it transports gas. Okay. Okay. So I put this note, PS, never forget the mechanical energy balance equation from chapter 2. Why? Because we will use this equation a lot in the subchapter. Okay, so the course outline will be divided into 3. First is pump, second is the gas moving machinery, the third is the compression of gases. Okay. Now, so I hope that you still remember these equations. Sorry. Yeah, where the actual shaft work equals to minus theoretical shaft work divided by the efficiency. Yeah, and both this WS and WP, they have the unit of joule per kilograms. Okay, now, okay, so now, yeah, to calculate, the actual brake power, because usually this is the actual shaft work. However, if we want to buy a pump, usually they will not say the actual shaft work. We will not use this term, the actual shaft work. Yeah, we will use the brake power. What is the power? What is the power? Yeah, they will not ask. Okay, I want to buy a pump. Yeah, and they will ask, what is the actual shaft work? No, they will not ask that. They will ask, what is the actual brake power? What is the power? Yeah, it has the unit of kilowatts or kilojoule per second or horsepower. Yeah, now to calculate this brake power, so we have to multiply the WP or the actual shaft work with the mass flow rate and convert the units such as in equations 3.3-2. This, the one on the left. Yeah. So this how you get the actual brake power. If you want to use the unit of watt, you use the first one. If you want to use the horsepower unit, then you use the second one. Okay. And then, yeah, another term, we can also, it is actually rarely of being asked. Yeah. However, maybe Jankoplis wants you to know, how to calculate the the theoretical brake power, the theoretical one. So you use this equation, theoretical power equals to actual brake power in kilowatt times the efficiency. Okay. Okay. Now, another way to calculate the minus WS or the theoretical shaft work is to use the developed head of the pump or pump head, or we use the term of H as in the equation of 3.3-4, because sometimes some supplier will use the term of brake power, but some supplier will also use the developed head. So like, what is the power that you want to use? How many meter? How many meter? Yeah, they will ask meter. Meter is the term of meter is height, right? It's age. Yeah. Now, okay, so how can we calculate the theoretical shaft work if we know the pump head? Or vice versa, how to know the developed head if I know the theoretical shaft power? Yeah, then you can use this equation. Yeah, minus WS equals to 8, or the developed head of the pump, times the gravity. Yeah. Okay. Now, actually, these equations, have ever been used in chapter 2. Yeah, you can refer to this example 2.10-4 to refresh what we've discussed previously. Yeah, about developed head of the pump versus WS. Yeah, so maybe by oh, I want to know the brake power when I know the developed head of the pump. Yeah, then you can try to calculate the minus WS first, and then you use this equation, to know the brake power. Yeah, or if we know the brake power and we want to know the head of the pump, then we can use this equation to find the minus WS. Then we can use this equation to find the pump head. Okay. Yeah. Okay, so actually what is why they use M? Why they use developed head of the pump? Yeah, so actually this H refers to if we flow, if we use this pump, yeah, to flow the fluids. Yeah, like how many meter the fluid can go up. Yeah. Yeah, maybe I will try to wait a minute. I cannot make annotation. Please wait. Okay. Okay, let me try. Yeah. The pump, yeah. Oh wait. Why can I? Yeah, if I have a pump like this, yeah, and then I have a fluid flow coming into the pump, and then the pump will force the fluid to go up. Now, let's say the power of the pump is 10 kilowatt. Yeah. Then it can make the fluid go upward, up until it reaches the height of 10 meters. Yeah. Okay. Now, if I increase the brake power to 20 kilowatt, yeah. So the pump has a bigger power, right? So that means, yeah, it can push the fluid to come up until it reaches the height of 20 meter. Yeah, and it goes as well if we decrease the power. Okay. So that's how we use developed head of the pump. Yeah, because some supplier will use this, some supplier will use this. Yeah. Okay. Nah. Okay. So we go to the next slide. Yeah. Nah. Okay, so we have a special case for pump. Yeah. Sorry, for fan. Yeah, for fan. Yeah, so this is a special case if we regard fan as a mechanical device to move the incompressible gases. Yeah. So for calculation of a fan power, yeah, with the delta P is less than 100 millimeter of water, so you can use this equation below. Yeah. So if you regard the fan as a mechanical device to move the incompressible gases, since the delta P is not very high, it's only like 100 millimeter of water, then you can use this equation. Yeah, you can see example 3.3-3. Yeah. Okay. Yeah. Later we will discuss this, but let's move to the next subchapter first. Yeah. Okay. Now, okay, we're going deeper. Okay. Pumps are usually driven by electric motors. If they don't have electric motors, then we don't know where the energy comes from. Yeah. Now, to calculate the total electric power input, yeah, that is needed. Now, the efficiency of electric motors, or efficiency E, yeah, must be taken into account. Yeah, so we must use this term in the calculation. Yeah. Okay. Now you can use this equation 3.3-5. Yeah, to calculate the total electric power input needed. Yeah, then we must to put, yeah, this term, yeah, in the equation as well. Yeah, nah, how do we know the value of this term? Yeah, you can use this table, yeah, for the typical efficiency of electric motor. Yeah, so if the electric motor power is only 0.5, then the term is 77% or 0.77. If the electric motor power is higher than is reaching 50 kilowatts, then the term becomes 90% or 0.9. Yeah, you may use the interpolation for value in between these values. Okay. Okay. Nah, nah. So we move to the next subchapter about suction lift of pumps or NPSH. Yeah, or it's actually the abbreviation of net positive suction head. Net positive suction head. Yeah. So what is it? Yeah. Okay. So here's the story. Yeah. So first, pump can work when the absolute pressure, yeah, in this part. So actually for pumps, they have two parts, yeah, two lines, suction line. So let's say this is the pipe and we put pump here. So the suction line is in this part. And then, as I said previously, the pump actually will push the fluid upwards, right? Will push the fluid upwards. Now, the upward flow here, we call it as a discharge line. Yeah, so suction line is before the pump, discharge line is after the pump. Now, pump can work when the absolute pressure, yeah, in the suction line here at least equal to the vapor pressure of liquid at their respective temperature. So let's say we move water at 80 degrees Celsius. Yeah. Nah, the pump, yeah, can suck, yeah, yeah, the pump can suck the water, yeah, when the pressure in this part is the same as in the water at 80 degrees Celsius. Yeah, if it's below that, then the water cannot move. Yeah, cannot move upward, cannot be sucked. Yeah. Okay, so it has to be at least equal to the vapor pressure of liquid at their respective temperature. So if we have water at 80, then we can find actually the vapor pressure of the water at 80 degrees Celsius. So if it reaches that value, then the water can start to move, yeah, being suctioned into the pump and discharged upward. Yeah. Now, however, if the absolute pressure in the suction line is lower than the vapor pressure of the liquid, yeah, so that means, yeah, there is no liquid passing through the centrifugal. Yeah. Now there will be a phenomenon called cavitation. Cavity. Kalau bahasa Indonesia kekosongan. Ya. Where liquid flushes into vapor. Kalau kita biasanya ngomongnya kosong, ya, pompanya kosong. Okay? Yeah, it's because the liquid flushes into vapors. Yeah, nah, this cavitation causes no more liquid in the pump. Yeah, that's why I said kosong, empty, and subsequently causes the pump vibration. Yeah, so it will be broken then. Yeah. Now, to avoid this two, cavitation and pump vibration, yeah, the absolute pressure in the suction line must be greater than the vapor pressure of liquid and exceed it, yeah, by the value called NPSH, or R stands for required. Yeah, okay, so that this NPSHR, yeah, will make sure that the absolute pressure in the suction line will be higher than the vapor pressure of liquid. Yeah. Nah, and moreover, yeah, pumps manufacturer must design a pump with higher NPSH, at least 1 meter or 3 feet than NPSHR. Yeah, this value is called NPSHA, where A stands for available. Yeah, so so when we have an when we add, yeah, yeah, when we have the NPSHR, yeah, when we I mean like this, I mean when we have calculated this NPSHR, yeah, then actually the manufacturer will exceed it a bit, yeah, will exceed it a bit, yeah. Why? So that it not goes down below the required NPSH. Because if it's go down below the value of NPSHR, then the pump will prone to cavitation and pump vibration. Yeah. So after we calculate, oh, I know the NPSH that is required. Yeah. To avoid this cavitation and pump vibration, let's say it's 10 meter. Let's say 10 meter. Yeah. That means, yeah, the manufacturer or the pump designer must design a pump with NPSHA of 11 meter. Yeah. So that it's just to make sure that it doesn't go below 10 meter. Because if the let's say yeah, there's nothing ideal. Yeah, there is nothing ideal in the world, right? So let's say, oh yeah, I know the NPSHR is 10 meter. Yeah. Okay, then I will design also 10 meter. But there is no thing that ideal in the world, right? So sometimes maybe it can have a fluctuation. Yeah. It can be go down below 10 meter. Then if it's go down below 10 meter, then the pump is prone to cavitation and pump vibration. So that's why the pump's manufacturer or the pump's designer will have to design the higher NPSHA. Yeah, by at least adding it by 1 meter or 3 feet at least. Yeah, so the design manufacturer can add 1 meter plus 10, so it's 11 meter. That's the NPSHA. Yeah, so that if there is a fluctuation occurred, yeah, during the process, then it will not, yeah, go lower than 10 meter. It will stay above the required NPSH. Okay. Okay. Okay, so this is the typical value for NPSHAR for centrifugal pumps to move the water below 100 degrees Celsius at 1,750 RPM pump rotation. Yeah. So for a pump with working pressure of less than 3,500 kPa or 500 psig, then when the flow rate is up to 200 gallon per minute or 200 GPM, the NPSHR is 1.5 meter or 5 feet. Yeah. The higher the GPM, yeah, the higher the volumetric flow rate of the pump, then the NPSHR will be higher as well. Yeah. So you can use this value, yeah, as long your condition meets this requirement. Okay, so for working pressure of 7,000 kPa or 1,000 psig, yeah, then when we have a flow rate up to 200 GPM, yeah, the NPSHR is 3 meter. Yeah, when the flow rate is at 2,000 GPM, the NPSHR is 6.6 meter. Yeah, you may use the interpolation for value in between. Okay. Okay, so Miss, if I have a flow rate of 100 GPM, or the working pressure is 2,000 kPa, I move the water with the temperature of 60 degrees Celsius, and I have the pump rotation of 1,750 RPM. Then what is the NPSHR? This 1.5, because you have to see this, yeah? When the flow rate up to 200 GPM, up to, so below 200 GPM, then you can use this. But for this, it's at. This is actually at, not at 2, yeah? At, okay? Nah, and then, okay, if I have another rotation, another pump rotation, yeah, at 3,550 RPM, yeah. Now all this NPSHR can be increased by a factor of 2.2. So you can just multiply, yeah, it by 2.2. Okay. Nah. Now, to calculate NPSHA for a system like in the figure of 3.3-1, now we can use equation 3.3-6, yeah, where P1 is the pressure above the liquid surface, PVP, yeah, is the vapor pressure of liquid at given temperature, C is height of the liquid surface above the pump center line. Now, in this case, GZ1 is the static head, yeah, and then the velocity of fluid in pipe, yeah, we use the term of V, yeah. Now this term we call it as a velocity head. So this is static head, this is velocity head, okay. And then the total friction, yeah, in the suction line or before the pump, yeah, if the process is the same as this figure, then the total friction comes from the sudden contraction, straight pipe, and one fitting, yeah, elbow 90 degree, yeah, sudden contraction, straight pipe, and then one fitting, elbow 90 degree. Now we call this sigma F as friction head. Okay, so if we have a figure like this, then we can use the equation. Now, okay, maybe before I go to the next point in our PowerPoint, yeah. Now, how about if I have a tank, yeah, this tank is not above the pump, okay? The pump is above the tank. That means the Z1, yeah, the value of Z1 is minus, okay? The value of Z1 is minus. Yeah, this is plus, yeah? This is plus, yeah, let's say this is 5 meter above the pump center line, 5 meters. So Z1 is 5 meters. 5, yeah, plus 5, okay, positive 5. Now, if the pump is higher than the tank, that means, yeah, the Z1 is, yeah, negative, yeah, because the top of the liquid is lower than the pump center line, yeah, so it will be minus, okay. Now, okay, so we go to the next point on the PowerPoint. As mentioned before, yeah, NPSHA is always higher than NPSHR, yeah, by minimum 1 meter or 3 feet. Now, for cold, now this is a special case, yeah, for cold water and cases where all terms in this equation are small except for P1, and the process is carried out in atmospheric pressure, then the NPSHA can be directly set at 10.3, yeah, or 33.9 feet. Okay, so we go to see the example 3.3-1. Oh, okay. So I will go directly, yeah, to this part, yeah. Okay, so I have water, yeah, at 50 degrees Celsius in an open tank at atmospheric pressure. the pump is 3 meters above the open tank level. So that means the pump is above this surface of the water. Yeah. Now the velocity in pipe is 0.9 meter per second. The friction head loss in the pipe has been calculated as 1 meter. The required NPSHR for this pump is 2 meter. Now we are asked to calculate the NPSHA. Okay, so from Appendix A2, yeah, that's for water, I can get the density, yeah, and I can get the vapor pressure of the water at 50 degrees Celsius. Yeah. And P1 is 1 atm. Why? Yeah, because it's an open tank. Yeah, open tank to the atmospheric. Yeah, so P1 is 1 atm. Yeah, we convert it to Pascal. And then we substitute all the known value to equation of 6. And that we know that C1 is negative. Yeah, because the open tank level is lower than the pump center line. Yeah, so it's -3. Yeah, and the friction head loss is 1 meter. And then for us, yeah, this is head, right? So for us to make it back, yeah, to joule per kilogram, then we have to multiply it by G, yeah, by gravity. Okay, so I put all of the value, known value that I can get, that NPSHA okay, sorry for the disturbance. Yeah. Okay, so I found that the NPSHA is 5.14 meter and the NPSHR is 2 meter. Yeah, as I said previously, yeah, NPSHA shall be higher than NPSHR by 1 meter. So since the NPSHR for this pump is 2 meter, then actually the minimum available NPSH given by the manufacturer shall be 3 meter. But yeah, the designer is generous enough, yeah, to give the NPSHA of 5.14 meter. Okay, so I will go to the next slides. Yeah, it's about the general type of pump. Yeah, we know centrifugal pump. Yeah, this is one of the most common pump. Yeah, that is used in the it is used in the industries. Yeah, now it's available at capacity of very low cubic meter per minute up until to a very high cubic meter per minute. Yeah, with a head of few meters to 5,000 kPa. So it's really widely ranged. Yeah. Now it consists of an impeller rotating inside a casing. Yeah, this one, as you can see on the GIF. Yeah, and the principle is liquid enters axially, yeah, perpendicular to the impeller, and then it spreads out radially between the impeller vane, and then finally it goes up to the discharge zone. Yeah, the rotation of impeller imparts high velocity of fluid and increase its pressure head. Yeah, so the more intensive the rotation is, then the higher the velocity of the fluid. And of course, yeah, the higher the pressure head of the liquid. Okay, now the performance of this type of pump is usually expressed by the characteristics curve shown in figure 3. Where is it? Let me check. Scroll it down. Ah, this one. Yeah. So this is the characteristic curve for a single state centrifugal pump. Yeah. So if you know the developed head, then you know the efficiency. If you know the efficiency, and we actually know the developed head. Yeah, if we know the brake horsepower, then we know the efficiency and developed head. Yeah. Okay. Nah, several centrifugal, okay, sorry. Yeah, for number 7, yeah, in this type of pump, yeah, the pressure is proportional to the density and head. Yeah, since density times gravity times height equals to P. So I can say that pressure is proportional to density and head. Yeah, rho and H. Okay, now brake power of pump is proportional to the density. Yeah. The higher the density is, that means we need a higher brake power as well. Yeah, you can imagine, yeah, if I move water and if I move a pace, yeah, let's say caramel, yeah, sugar caramel, yeah, sugar caramel, yeah, and water, yeah, sugar caramel has a higher density and also higher viscosity, right? Now, then we need a higher brake power, yeah, to move the sugar caramel, yeah, as compared with as we move the water, yeah. Yeah, because it's easier for us to move the fluid that is in lower density as compared with the higher density. Now, when viscosity is less than 50 centipoise, it will have only a small effect to pressure head. Yeah, so if the fluid has a viscosity less than 50 centipoise, then this viscosity will not affect the pressure head. Yeah, but once it's higher than 50 centipoise, then the viscosity will also give a significant effect to the pressure head. Yeah, this is the several pump efficiencies for centrifugal pump. Yeah, again, you may use the interpolation for values in between. Yeah, now rough approximation for centrifugal pump can be seen in equation 7 up until 9. We call it as affinity law. So this one. Yeah. So if we have two states, yeah, then we can have a rough approximation. Yeah, let's say if we have two states, I know the condition in the first state, then I want to know the condition in the second state, then we can use this rough approximation. Yeah. And vice versa. If we know the condition in second condition, we want to know the condition in the first state. Yeah, then we can also use this. Equation. Yeah. The advantage of the centrifugal pump, yeah, it can deliver liquid in uniform pressure without any shocks or pulsation. Yeah, it's applicable to most liquid with a viscosity of lower than 50 centipoise. And it is also able to handle liquids with large amount of suspended solids that is suitable for chemical and biological plants. Yeah, this is not plants as if tanaman ya, bukan plants is a factory. Yeah, for a factory working a lot with chemical and biological, then this pump is usually their choice. Okay, we can see example 3.3-2. Okay. Okay. In order to see how the brake HP curve is determined, calculate the brake HP at 40 gallon per minute flow rate for the pump in figure 3.3-3. Okay, so we know that the GPM is 40. The efficiency, okay, so I will move up. Okay, so the gallon per minute is how many? 40. Yeah, 40. I know the efficiency. Yeah, how? By drawing a vertical line up until it crosses the efficiency curve, right? And it will give you a point here. Once it gives you the point here, then you draw a horizontal line to the right hand side, yeah, for efficiency. So it's 60. Then develop head, you draw a horizontal line to the left. It's 30 feet, around 30 feet. Okay. And then if you want to know the brake horsepower, then you can just draw a horizontal line up until this scale. Yeah, so it's like around 1.2 brake horsepower. Yeah. Okay, so it's like this, yeah. 60, the head is, previously I told you that it's like, oh sorry, develop head is like here. It's not here, yeah. The efficiency, so like this. 40, if I go to the efficiency curve, then I will get the efficiency. If I draw a vertical line up until it passes through the brake horsepower curve, then I will get the brake horsepower. Yeah, to this. Yeah, and if I also draw a vertical line up until it meets the develop head curve, then I can get the develop head value. Yeah, it's 38 point something, 60, and the brake horsepower is like some, I think it's like around 0.6. Yeah, around 0.6. Yeah. Okay. Yeah. And Gianco, please want to prove it. Yeah, want to prove whether the curve, yeah, can be directly used. Yeah. So Gianco, please use the general equation, yeah, to calculate the brake horsepower. Okay, so at 40 gallon per minute, the curve of efficiency reaches the value of 60%. The head is almost 40 feet. Yeah. And then the water, yeah. The water, yeah, they use the common density, yeah. 62.4 pound mass per cubic feet. Yeah. So by inputting all of this, yeah, by inputting the gallon and then the density, yeah, and then some unit conversion, then we can get the mass flow rate. Oh, the mass flow rate is this. Okay. By using the equation 4, yeah, 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 we can get the minus WS is 38.5. Okay. And then by using equation 2, go up again, then we can get the brake HP of the brake horsepower of 0.65. Yeah, the value is quite similar, right? Yeah, it's quite similar if we use this curve. Yeah, go up straight, and then once it passes through the curve, then we can get 1 point here, and then sorry, and then draw a horizontal line up until this part. Yeah, so it's like around 0.6, right? As I said previously, 0.6 horsepower. So Giancock is successfully proved, yeah, that the calculation using the general equation of pump agrees, yeah, with the value shown in the curve. Okay. Okay. Oh, sorry. So actually, I put it as well in this um in this slide. Okay, so I will go to the second general types of pump, which is the positive displacement pump. Yeah, nah, the positive displacement pump, yeah, can be divided into two. First is reciprocating, yeah, just like a piston, yeah, and the second one is a rotary pump, yeah. Okay, so for reciprocating positive displacement pump, it consists of a stationary cylinder, yeah, and a piston, yeah. So the principle, yeah, when the piston is withdrawn, the liquid is drawn into the chamber, and then once the piston push out, yeah, push the liquid out, yeah, then the liquid is forced out from the chamber by the piston on the return stroke, yeah. Okay. Okay, so when the piston is withdrawn, the liquid is drawn into the chamber. And then the liquid is forced out, yeah, from the chamber when the piston is on the return stroke. Yeah, so when the piston push the chamber, then of course the liquid from the chamber will go up, yeah, and has a higher pressure and velocity. Yeah. Now, for the rotary pump, yeah, the principle, yeah, the two gears rotate, yeah, and then the liquid, yeah, sorry. Okay, now the two gears rotate, yeah, and then the liquid trapped in between the two gears will be forced to discharge. Okay, now advantage of this pump, these two pumps, yeah, that they can be used to a very high pressure. Yeah, again, you can use equation 1 to 5, yeah, to calculate, yeah, this type of pump. Yeah, now the discharge flow rate depends on the piston speed. Yeah, depends on the rotary speed. Yeah. Yeah, if the piston speed or the stroke speed is higher, then of course the velocity and the pressure of the liquid, yeah, will be, the discharge liquid will be also higher. Yeah, it goes as well if the rotary pump, yeah, if the two gears, yeah, rotates in a higher speed, in a higher RPM, yeah, that means, yeah, the liquid will have a higher velocity. It will have a higher developed head. It will have a higher pressure. Yeah. Nah. Okay. So the brake power of these two pumps, yeah, depends on the pressure head, not the discharge rate. Okay. Now, and then these are the several pump efficiencies. Yeah. Again, you can use interpolation for value in between. Okay. Okay, so I will move to the second part, yeah, the second outline, which is the gas moving machinery. Okay, the gas moving machinery, yeah, comprises a mechanical device to compress and move gases. Okay, there are several types, yeah, as I said previously, fans for low pressure, blower for intermediate pressure, and compressor is for a high pressure. Yeah, this is a common industrial fan or a centrifugal fan. Yeah, it's used for low pressure, low capacity with a discharge head of 1 to 1.5 meter of water. Yeah, it is used to increase velocity of gases, but only slightly escalate pressure head. That's why if we stay near the fan, yeah, we can feel the wind, yeah, but there is no pressure head. There is no pressure coming to us, right? We are not feel suffocated, right, because of the pressure. We can only feel the wind. So it increased velocity of the gases, but it only slightly escalates pressure head. So the principle is similar to centrifugal pump. Yeah, so the rotor induces the centrifugal force that causes a compression of gas. And then this compressed gas, this gas compression increases the velocity at the discharge point. Yeah, okay. So the compression, yeah, this is static pressure head. This compression increases velocity, this is velocity head. Okay, now this is the operating efficiency is 40 to 70% affected by the static pressure head and also the velocity head. Yeah, the operating pressure of fan, yeah, equals to the velocity head plus static pressure head of a discharge gas. Yeah, so you have to calculate, yeah, velocity head and static pressure head. Sum it up, then you can get the operating pressure of fan. Yeah. Now, for calculation of power, yeah, you may use the equation in slide 5 for incompressible flow. Yeah, because fans will not change, will only change the pressure head a little bit. Yeah, so we can say that this fan, yeah, moves the incompressible fluid. That's why we can use equation for incompressible flow, yeah, as our equations to calculate the power of this fan. Yeah. Okay. Okay. So I will go to the example of 3, the brake power of centrifugal fan. Yeah. I will go up to slide 5, I think. Okay, yeah, I will. Yeah, as I said, yeah, we can see from example 3.3, that's 3, yeah, for this special case, yeah. It is desired to use this volumetric flow rate of air, yeah, in a process, yeah, the amount of air which is at rest enters the fan suction at pressure of this and discharge at the pressure of this. And we also know that in the suction line, the temperature of the air is this. Yeah, the velocity at the discharge line is this. Okay. And then the centrifugal fan, having a fan efficiency of 60%, calculate the brake kilowatt power need. Okay, incompressible flow can be assumed since the pressure drop, yeah, is only, yeah, so from discharge minus inlet, yeah, suction line. Only 3.8% of the upstream pressure. Yeah, so it can be assumed as a incompressible fluid. Yeah. Now, the average density of flowing gas, yeah, since for gases, yeah, the density changes, yeah, during the process, yeah, the pumping process, yeah. So we can actually use the mechanical energy balance equation like this, yeah. Now, this is density average, yeah, density average, yeah. Okay, so from the inlet and the outlet, yeah, they will have different density, right? Even though maybe not differ too much, but it is different. So we can calculate the density at the first point, yeah, at the inlet or suction point. Yeah, we can use this equation. Yeah. Okay, so it's 0.94. Yeah. And at the discharge, yeah, we can actually just use the ratio of the pressure, yeah, to get the pressure at the discharge point. Comes this. Yeah. This one is actually PVNRT. Yeah, PVNRT. Yeah, if you see it's PVNRT. Okay. Now then I can calculate the average density of the gas. Yeah, 0.95 P. Not too much different between the two. Yeah, but since it changes, then we shall calculate it. Yeah, so we will put this value to here, the density average. Now, the mass flow rate of the gas, yeah, we can use this equation, yeah, to find the mass flow rate. Yeah, this is the volumetric flow rate. This is the unit conversion. This is PVNRT. And then, yeah. Yeah, and this is the molecular weight. Yeah, so that we can get the kilogram per second. Okay. So the developed pressure head. So this one. Yeah. Yeah. So it's the delta P divided by the density average. Divided by the density average. Don't forget to convert the units first. Then we can get the developed pressure head. The developed velocity head, the first term here. Yeah. C1 is 0. Yeah, why? Yeah, because when we use the fan, yeah, at first, the velocity of air, yeah, is at rest. Yeah, once it passes through the centrifugal fan, then it has a velocity. Yeah. So V1 is 0, V2 is 45.7. So it becomes like this. And then writing all general mechanical energy balance equation like this, right? Like this. Yeah. We set the Z1 and Z2 equals to 0. Yeah, because usually for a fan, yeah, they will just move the gas around, yeah, not go upward, but just passes, yeah, in the same elevation, right? Yeah, let's say if you have fan, yeah, on the left side, yeah, is the suction line, yeah, and then on the right side is the discharge line. Then the gas is actually only move, only increase the speed, increase the pressure head, yeah, but it doesn't increase the elevation. Yeah, it just passes through the fence, right, in the same height. Yeah, yeah. That's why Z1 and Z2 equals to 0. Yeah, and then we solve all of this, then we can get the minus WS. We know minus WS, then we can use equation 2 to get the brake power in kilowatt. Yeah. Okay. um. Okay, so I will go next. Yeah, to the. Okay. 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 Yeah. So for centrifugal, so for blower, yeah, they have two types of blower: centrifugal one, or we call it turbo blower, and rotary blower and compressor. So for rotary, it can be blower, it can be compressor, depending on the rotary speed. Yeah, in the not rotary speed, rotation speed, depending on the rotation speed. Yeah. So centrifugal blower, yeah, is used to move large volume of gas with pressure rises from 5 kPa to several thousand of kPa. The principle is similar to pump. Yeah, only compressible fluid is moved instead of the incompressible one. Yeah, similar, right? The discharge line, yeah, can be go downward, can be go upward. Now, the head of centrifugal blower does not depend on the fluid handle as long as the viscosity is less than 50 centipoids. Yeah. And if we want to go to a higher pressure, then sometimes the centrifugal blower will be used in a multi-states, yeah, to reach a higher pressure. Okay, now, now another type is rotary. So it's positive displacement again. Yeah. It can work in a constant volumetric rate with variable discharge pressure. Now, volumetric rate depends on the rotary speed. Yeah, the rotation speed. It can increase the pressure up to 1000 kPa. Yeah, oh, that's all. Okay, so for rotary is only that one. And for the piston, yeah, it's used for a very high pressure. Yeah, it can reach to more than 10,000 kPa for multi-stage reciprocating compressor. Yeah, the principle is the same. Yeah, just like the pump. Yeah, now in all blowers and compressor, yeah, yeah, we will use the compressible flow equation, which is in the next topic. Okay. If you have any question, then you can just directly drop the message, yeah, to my WhatsApp, or you can drop the comment in this YouTube video, or maybe you can just ask me during our physical class. Okay. Nah. Okay. So for compressible flow, yeah, the mechanical energy must be written in the differential form, yeah, because the velocity changes, yeah, over the process, yeah. The z also changes over the process. This is compressible, yeah, not incompressible. For fan, dz is 0, yeah, because as I mentioned before, yeah, that why I cannot write, why I cannot annotate it, yeah. Okay. Now, let's say I have a fan, yeah, yeah. Oh, why my drawing is so bad? Okay, so I have a fan placed on the first level, yeah, or the first floor. Yeah, if I say it's you will feel it in the second floor, then usually they will have a closure, yeah, between the first and second floor. So that's why I use an example of mezzanine. Sorry. Wait. Let's say okay, so this is the fan. This is the fan. And then you are here, yeah, on the mezzanine level. And then one of you are in the first floor, yeah, in the mezzanine level. This is actually what I told you during the discussion of example 3.3-3. Yeah, but I will repeat it, yeah, so that you can be more understand with this concept. Yeah. So when the fan, yeah, is turned on, yeah, then actually the people in the first floor can feel the wind comes from the fan because they are in the same level. Yeah. Yeah. Nah, but mezzanine level, yeah, usually is an open space, right, connecting to the first level. Yeah. Nah, so you are placed higher than the fan. Yeah. But actually, the air between the mezzanine level and the air in the first floor is connected to each other. Yeah, because it's an open space. Yeah, but can you still feel the wind comes from this fan? Yeah, that's why I said I think you can barely feel it. Yeah, because you are not in the same level. Yeah, you were placed higher than the fan. Yeah, okay. Apalagi, yeah, if you are placed in the second level where the closure is there, yeah, then I believe that you cannot feel anything. Yeah, you can't even not knowing that the fan is turned on. Yeah, because you are placed in the different level and with a closure. So that's why when we discuss about the example 3.3-3, yeah, when we want to calculate the power of the fan, yeah, we usually assume that the delta Z, yeah, is 0. Because the one who can feel it, yeah, is usually the one that comes from the same level. Yeah. Nah, but this, yeah, is only applicable for the incompressible gas. Yeah, incompressible gas or the gas that passes through the fan. Yeah, but the gas that passes through the blower or the gas that passes through the compressor will usually have delta Z. Yeah, for the incompressible gas or gas that passes through the fan, the delta Z is 0. Yeah, but the gas that passes through the blower and compressor will elevate, yeah, in height. Yeah, okay. Uh, okay. Yeah, nah. So we will write it in differential form because velocity, height, pressure, friction, yeah, will all changes during the process. Yeah. Now, however, in this part, yeah, for compression of gases, yeah, the simplified mechanical EB will be used where the velocity head term, static head term, and friction term are dropped. Why? Why? Yeah, like this. Yeah, so what's left is only W with dp per density. Yeah, yeah. Why? Because, yeah, the friction term, the static head term, the velocity head term is insignificant when we compare it to the change of the pressure. So the dp per density, the value is much, much higher, and it affects in a higher significance, yeah, to the WS. Yeah. So when you compare F with P for density, yeah, FF is insignificant. C times G is also insignificant compared to dp per rho. dv square over 2 alpha is also insignificant if we compare it to the dp per density. That's why we can neglect all three terms. That's why we are left with the dp per density equals to delta work, yeah, delta WS. Okay, now, okay, so like this, yeah. Now, okay, so there are paths of compression. Yeah, so first is isothermal compression. During the compression, the temperature is maintained the same by cooling. The second one, diabatic compression. So during the compression, no heat or mass transfer, and process is always reversible. Yeah. For polytropic compression, so a compression where heat transfer and temperature change take place. So it's non-adiabatic, non-isothermal. That's polytropic. Okay, so we go to isothermal compression. So where the temperature during compression is the same. Yeah, T1 equals to T2. Yeah. So since it's gases, yeah, so we can use PV and RT, right? So if we have a first condition, yeah, with P1, V1, M1, T1, yeah, and then I have also the second condition, P2, V2, M2, T2, yeah. Yeah, during the compression, is there any mass change? No, but is there any volume change? Yes, yeah. So that's why they change, yeah, the M and V to become density. Yeah, M per V is actually density, but once we put it on the left hand side, then it becomes per. Yeah, it becomes per density 1. Okay, equals to RT over M. M is the molecular weight. It goes as well for the second condition. Yeah, PV equals to N RT, right? N is mass over molecular weight. Yeah. And then we move the M2 to the left-hand side, so it becomes 1 over density 2. Yeah. Actually, we can delete this M1 and M2. Yeah, because in the compression, there is no change in mass, actually. Yeah, but since the density changed, then Jacob use this equation, the equation with density in it, yeah, equals to RT2 over M. Now, since T1 equals to T2 or equals to T, then RT over M is constant. That's why equations 12 can be used. P1 over density 1 equals to P2 over density 2. Yeah, Or if I can say in a more general manner, P1 over P2 equals to P over density. Ya. Nah, okay, nah. Okay, after some substitution, then we can get the minus Ws during the isothermal compression can be calculated using this equation. So we put this into this, yeah. So we can get this, yeah. Yeah, it's only using the simple integration. Yeah. Now, and the break power can be calculated using equation 17. I will go down first, this one. Yeah. So once you can get the minus W isothermal during isothermal compression, then you can get the break power using this equation. Okay. Yeah. Now, that's the isothermal compression. For the adiabatic compression, that means, yeah, the Q equals to 0. Yeah, it's the same like in the chemical engineering principles. Yeah, adiabatic means there is no mass or heat transfer between the system and the environment. So Q equals to 0. It follows isentropic condition or delta S1 equals delta S2. Yeah. Now, similar, yeah, actually you can use this. However, there must be an isentropic exponent constant added to equation. So that's why, sorry. So that's why, yeah, this the isentropic constant. Yeah. Yeah. Sorry. Oh, sorry. Yeah. It's not similar to equation 13, but similar to equation 12. Yeah. Similar to equation 12 can be used actually. However, there must be an isentropic constant here. Yeah. Which is gamma. Yeah. And this gamma is expressed as Cp over Cv. Yeah. Oh, that's why. Yeah. I use the equation from the third. Oh, no, 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 no. No, 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 no. No. I use the John Copley's fourth edition for this. Yeah. So, yeah, by putting it, yeah, by putting this equation of 14, yeah, to this equation of 11, yeah, then we can actually acquire equation 15 to calculate the minus Ws in a diabatic compression. Yeah, and then for calculating the break power using again equation 17. Now to calculate the correlation of the adiabatic temperature. So in a diabatic compression, there is a temperature change, but there is no heat transfer from the system to the environment. But there is a temperature change. So that's why if you want to calculate the diabatic temperature after and before compression, then you can use this equation. Now, value of gamma, yeah, that can be seen here. Yeah, so 1.4 for air, 1.31 for methane, and so on and so on. Yeah. Now, for the same compression ratio, yeah, this is an important note. Yeah. For the same compression ratio, the power needed for a diabatic compression is always higher than the power needed for isothermal compression. Therefore, sometimes in a diabatic compression, cooling is needed. Yeah, cooling is needed in the diabatic compression. Yeah. Okay. Oh, okay. Yeah. Okay, so for this example, I think I used from the third addition, yeah, but for the other equation, I use the fourth edition of John-Copley's, yeah. Okay. So from example 3.3-4 in fourth edition of John-Copley's, yeah, we are asked to calculate the compression of methane. I have a compressor, single states, to compress this kilomole of methane at this pressure and this temperature. And the discharge pressure is set at this 551.6 kPa absolute. We are asked to calculate the power required if the mechanical efficiency is 80% and the compression is diabatic. And then the second one, repeat, yeah, but for isothermal compression. So for part A first, we know P1, we know P2, we know methane, the molecular weight is 16, sorry. T1 is this. So I can get the mass flow rate. Yeah, I use the PV-nRT again. Yeah, the modified PV-nRT so that I can get mass. Okay, so I get mass. And then I know that for methane, yeah, from the previous slide of mine, I put that the methane, the gamma for methane is 1.31. And then the P2 over P1 ratio is 4:1. Yeah. So I put all of the known value here, gamma 1.31, RT1 over M, T1 I know from the problem, R I know, M I know. P1 over P2 is this, 4:1. Yeah, and so on. Yeah, so I can get that the minus WS is this. Okay, and then calculate the power, right? So I have to calculate the brake power. So I put all the known value here, minus WS, and then M from above. The efficiency is 0.8 times 1000, then I know that it's 52. Okay, so the second one, yeah, I will use the equation of 13. Yeah. Again, I put all the known value. And I get that the brake, the minus WS is this, the brake power is this. So it's lower, right? As you can see, the adiabatic power is always higher than the isothermal one. That's why usually for a diabatic, the diabatic compression requires cooling. Yeah. Okay. And then, okay. Okay, and then the third types of compression is polytropic compression, where heat transfer and temperature change occurs. So for polytropic compression, usually the data are obtained from experiments. Yeah, therefore, pressure and density at point 1 and 2 are usually known from the problems, while the unknown is the value of N here. So similar to the adiabatic, if adiabatic, we have gamma. Yeah, in polytropic, we have N. Yeah, but usually, if in adiabatic, the gamma is known, N here is unknown. Yeah, the P and the density is the one known for this polytropic compression, and vice versa for the diabatic compression. Okay, now you can use this equation to find the value of M. Yeah. Okay, and then the last one, yeah, the multi-states compression ratio. So if I have a multi-states compressor, yeah, usually water cooling is aided in between the compressor, not only at the end of a series of compressors. Sometimes compressor cooling, not compressors, 3 compressors and then cooling. No, usually compressor cooling. Yeah. Why we add the water cooling in between the compressor? Yeah, it's because so that the power required for each stage of compressor is minimum. Yeah, if we put the water cooling only at the end of the series of compressors, then usually the power required for each compressor is higher. Yeah, so that's why in industry, cost is one of the most important things. Yeah, that's why to reduce the power required for each compressor, then the water cooling is added in between the compressor. Now, the total power, yeah, will be also minimum if the compression ratio in all states is the same. Yeah, so the total power will be also minimum if the compression ratio in all states is the same. So if the first compressor increased 10 times the pressure, then the second one 10 times the pressure, the third one also 10 times the pressure. Yeah, it's 1,000 times the pressure, right? And then we compare it with 20. The first compressor 20, the second compressor 5, the third compression 10. Yeah, from the initial to the final, it's the same 1,000. 1,000 times pressure increase. Yeah. Yeah. But the one that gives the minimum power is the first one. Yeah. Is the first one. Yeah. Now, to calculate the compression ratio in each stage for n stages, yeah, we can use this equation where P1 is the inlet pressure, Pn is the outlet pressure after n stage. Yeah. PA and PP is the compression ratio in each stage. Yeah. So maybe I will try to annotate again. Yeah. Okay, so if I want to if I want to increase the the gas, the pressure of the gas from 10 kPa, yeah, to 10,000 kPa. It's 1,000 times higher than the first inlet pressure, right? Yeah, so we have to increase the pressure of the gas 1,000 times, right? Now, for the first case, yeah, for the first case, the compression ratio is 10 times here, 10 times here, 10 times here, okay? So it becomes 100 kPa here, 1,000 kPa here, and 10,000 kPa at the last one. Yeah, okay. Yeah, it's 10,000, it's 1,000 times, right? And then I have another case. Oh, why I cannot? Again, 10 kPa and 10,000 kPa. It's also 1,000 times, right? However, I increase it by 20 times. And here, 5 times. Here is 10 times. Yeah, it becomes 200 kPa. It becomes 1,000. I cannot. Okay, 1,000 kPa at this point, and then 10,000 kPa at the last point. Yeah, the same, right? However, the power required for the second case higher than the power required for the first case. Yeah, because of this theory. Yeah, why I can, because of this theory. Yeah, the total power will be minimum if the compression ratio in all states is the same. Yeah. Okay, I hope that it clears, yeah, up the theory. Okay. If you don't have any questions, yeah, then thank you very much, yeah, for contributing to these online courses. Yeah, I will meet you again with the subchapter 3.4 about agitation and mixing. Okay, thank you very much and see you next time.